Okay, so let me just take you back a couple of slides just to recap what we did. So we talked about some very simple compartmental models, okay, and we started with this one, one of the first which is made in the context of malaria. And one of the things that I tried to emphasize was that, one of the points of a very simple model are to conceptualize the problem, to point out certain key combinations of parameters that might be interesting. And one of the things that we came up with, which these compartmental models have kind of shown, is that there is a certain threshold above which an infection spreads and below which an infection will not spread. And that threshold, and quite logically, has to do with on average, how many people an infected person will infect before they recover in a population where they're all susceptible. So that's some basic property that tells you, is this infectious disease in this context even capable of spreading? And over time, of course, as the infection spreads through the population, the number of susceptible people decreases. So the effective reproduction number is what becomes relevant. And that starts from high, wherever it started when the infection was spreading, comes down, may come down to 1, may come down below that. But so these are all qualitative features about a spread of an infection, and one can understand some of this from a simple model. But as as we were saying, people are really interested in making more detailed predictions, as you all saw during COVID, right? So, and it turns out that, of course, a very simple model like Ross's first model is not capable of making very detailed predictions simply because it misses out many things. And a couple of people, subsequently made more complicated models and so on. So in the rest of this talk, I want to give you a sense of how people complicate these, how they try to predict, what can go wrong with predictions, okay? And the kinds of things that, apart from that kind of prediction, what people try to do. So we talked about, two types of, one way in which you can start to think of different possible ways you can make compartmental models is to think about immunity. So immunity is a question you have to ask about any disease you're trying to model. Is there immunity? How long does that immunity last? And it might, in these two extreme cases, lead to a situation where there's no immunity, this kind of a model, or where there is permanent immunity, which is this kind of a model. But there's other ways in which compartments can and have been added to these kind of models. So one thing, as I was mentioning earlier here, is that these models sort of realized that one of the things missing in this malaria model was the latent time, the time for which you get infected, but you haven't developed the disease enough to be infectious to another person or another mosquito. So one way is to take an SIR model and add another compartment. So one way to deal with these kind of time delays is to put in extra compartments. So people do this. This is also a very commonly used model, SEIR, where you have a susceptible person, when they get infected, go into a state where they are not yet infectious. There's a certain amount of time for which they are developing the disease and are not yet infectious. And then they become infectious and can catalyze further infections and further recoveries, okay? And now this process can go on, depending on what you're looking at. Here is a more complicated compartmental model that has been used for COVID modeling, for instance. So there's the S, there's that exposure, and then you can get either asymptomatic people or symptomatic people, okay? Now, yes?
Sorry, just Sandeep, of course, it's important to have a lot of variables in a model, but the more and more variables you're going to add, you need that many parameters.
Absolutely.
You need
absolutely. So I'll touch on that point. That's very much relevant. So let's just talk about the different ways in which people complicate these models, and indeed this problem will arise, and I will explicitly touch upon it. So what happens over here? So why do people add compartments like this? It's because this is a phenomenon that has been noticed as part of the disease. So in COVID,
sorry, one more quick question.
Please.
So you're calling these consistently compartment-based models. How is it different from a state-based
Yeah,
I mean,
it's not
it's the
really.
same thing.
These are states.
Yeah, because those are just probabilities and states.
They are states, indeed. It's just a convention that they call compartmental models. So exactly, like I said earlier, these compartments are really abstract. They're not actual compartments. In fact, this whole system is imagined, if anything, all these people are in a single room and interacting with each other. And we'll come back to how people complicate that, where they start to say, okay, it's not well mixed. All right, so so why put in more things like this? So here we have, here is a COVID model where they had asymptomatic people, symptomatic people, then symptomatic people who got mild form of the disease, serious form of the disease, hospitalized people, dead people, etc. I mean, you can in principle infinitely complicate this, right? You can imagine how you can put in more and more states. But the point is, if you actually want to keep track, if you have data, or if for some reason you want to. So in particular, this model started off, I think, mainly because people were trying to think in terms of COVID, the existence of a lot of asymptomatic people and how that would affect in the context of testing and so on. If you don't even know someone has the disease and doesn't have symptoms, how would that affect various kinds of interventions? So depending on the kinds of questions you're asking and the kinds of predictions you want to make and the kind of data you think you might have access to, people complicate it. But this is one extreme. I mean, in some ways, I wanted to show you this as an extreme, going from this very simple one to a much, much more complicated one, which has many, many compartments and many states. But as Uma said, when you have many such compartments, you have to keep track of many states. And as you can see, the number of parameters has increased so much. We, in the end, had just one parameter. But even here, we had sort of like 3 parameters. Here you've got the rate at which you go from there to there, the rate at which you go out of this, you develop symptoms, the probability that you develop symptoms or you don't, the chance that you get a serious disease or not, the chance you get hospitalized or not. I mean, it's just clearly, as you put in more compartments and more arrows, everything comes with 1 or 2 parameters, and the number of parameters really goes up. Okay, so keep that in mind, we'll come back to that. Another way in which people start to complicate these things is to add age structure. So we know, again, using COVID as an example, that even if everyone was in one room, not everyone was being affected by the disease in the same way, right? We know it affected people of different age groups differently. In many ways, in one way in which age structure comes in is in terms of the effect of the disease. Okay, so in terms of how many got a serious version of the disease, how many got mild disease, how many were asymptomatic. This was clearly age dependent, and it's something we discovered as COVID progressed. The children were getting milder cases of the disease, or not even getting not disease, or were asymptomatic. So many of these parameters might depend on age. Now, if you want to put that in, and this becomes important, and especially if you want to start thinking about interventions and which groups of people to protect and so on, you need to start dividing your population into age. So that now adds another set of compartments. So within every compartment, so effectively every compartment is split into now, say 10 compartments of where each compartment is also a different age. So now the number of compartments is not like 7 or 9 or whatever it was here, but it's 9 into 10. It's like 100 compartments. And again, as Uma was saying, that means a concomitant increase of the number of parameters. But another way in which age structure comes in all this is in terms of the contact probability. So remember the transmission, we were talking about these transmission parameters, beta, right? The transmission was something to do with contact, how often one interacts, and how often an infected individual interacts with one of you, how many handshakes I make with you, but also the probability of transmission, right? So even if the probability of transmission is the same, it could also be that amongst this group, I end up, if I'm infected, I don't handshake with everyone uniformly, but maybe there's an age structure to that. Maybe I interact with a certain age group more or less, and therefore, if you know that that's happening, then do you need to bring that in? So there were people who started taking these complicated models, already complicated models, and adding age structure, and then adding contact structure on top of that, which is, of course, taken from somewhere. So this is, I forget where this data is from, but I think it's from Pune, I think. But anyway, so some people have measured. For instance, in schools, obviously, in schools, kids interact mostly with other kids. Of course, they'll interact with teachers, but there are proportionally much less. So most contacts are between younger age groups. In workplaces, most contacts are between, adults. There aren't too many people who are very old or very young in a workplace. There will be a few, but on average, and such like. So you can take these kind of contact matrices and put them into this kind of parameter, beta, if you have the age structure. So people have done this. There are models out there that try to take this kind of contact structure into account. Okay, so the next thing, obviously, since we already talked about how these contact matrices can be different in different locations, right? Schools are different from workplaces and so on. You might want to actually put in these locations. So far, all the models, compartmental models I talked about were this, right? They were well mixed. Well mixed means essentially everybody has access to everybody else. If there is an infected person and there's some number of susceptible people, there is some probability that this infected person will run into all of those susceptible people given enough time. But that may not be true in a real population. In a real population, we don't well mix with everyone, right? We have our little groups, we have our locations where we are. Within locations, perhaps we are reasonably well mixed. In our homes, we meet everybody we usually meet in our homes. In our workplace, we meet a number of people we meet in our workplaces and so on. So you could imagine that a real population is actually subdivided into many locations, each of which are well mixed, and within which a compartmental well-mixed model is sort of running. But then people move from location to location. You go from home to work, work to home, home to school, back, etc., right? So people have taken these models and further complicated them and put them in this. Now you can imagine within each of these locations, there might be further age structure and further contact matrices. So you can really imagine how, now you can really see how parameters are really exploding. Not only do you have to describe this structure of the network, these are now called network models, okay? So if you see something which says a network model, that means you have these different kinds of locations. So now you have to not only describe what kinds of locations there are, how many there are, how many interactions there are between these locations, so what are the rules by which people move, everything is more parameters, right? So every increase is more realistic, but comes with more parameters. But people have tried to do this, and people have tried to independently estimate, how many workplaces are there in say a small town, and how many schools are there, and how many hospitals are there, and how often people move between these, and try and put this in, okay? Okay, another complication which we touched on briefly, yes?
Yeah, so you mentioned, like, for example, age can be added to all separate compartments, yes, like theoretically.
Yeah.
But that will just complicate the model a lot.
Absolutely.
So do people first just go out and collect data which all compartment really makes sense? I mean, where adding age would make more sense.
Yeah, so, in the context of these age structure things, I mean, it didn't make much sense to make models like this until there was some amount of data about, how various parameters would change with age, until there was some data about how different age groups interact. But see, certain kinds of data was already there independently from completely other studies. So for instance, the contact matrices, people have been studying that for their own reason, not necessarily infectious disease reasons, but for other reasons. So, in the context of COVID, for instance, people were just looking around for what data is there. And in some sense, some of the models and some of the complications added to the models were dependent on what data was already present. And some was dependent on data as it got produced. So especially things like the way the disease affected younger people is something we discovered along the way. And as measurements and as more and more examples came up, being able to pin down those parameters and how various parameters change, let's say the chance of being asymptomatic, how that is dependent on age, that what precise values to put or what precise ratios to put, that is something people didn't know initially, knew only qualitatively initially, and then over time it became a little more quantitative. And even when it's quantitative, it might be in a certain context, and in a different country, in a different place, it might be different, right? So it's sort of, people kind of, my point is people want to make more complicated models when they want to make more specific predictions. But exactly as Uma was saying, when you want to make more complicated models, you have to deal with the fact that there's more parameters, and you can only do it sensibly if you have access to data where you have at least enough reliable data to get some sense of those parameters. If not a precise value, but at least a range, then at least you can explore a range.
For example, like at the other end of complexity is agent-based models, where every single individual in the population is modeled, right? Like Shivatreya, who's actually at ICTS, and others did for Bangalore City.
So exactly, and that's where these that's exactly what I was just about to come to. So that's the extreme. So, noise and stochasticity is what we talked about. Noise and stochasticity is about, so far all these models have sort of been treating things as average, right? Average rates and so on. The noise comes, as we discussed, because each individual event of infection is a stochastic event. There's a chance element in it. So if you really want to take all that into account, you have to now start doing individuals, right? You have to actually take into account specific individuals. There's stochasticity at so many levels. It's not just at the infection. But if you're already talking about a network model with many locations and people moving, there's also stochasticity and chance elements in who moves when. Okay, some of us go deterministically back and forth to work, but not everyone, not all the time. There is stochasticity there also, right? So every element that's added also has probably a stochastic element along with it. So indeed, the other extreme has been these agent-based models, as you were saying, where you're trying to, really. So one extreme was a single location, a single room, and the population is in that room. You forget about all the ages, forget about everything. They're just susceptible, infected, recovered, or just susceptible, infected. That's one extreme. The other extreme is you take everybody in a certain, whatever, city or town or whatever, and you're actually trying to model every single person and every single location they could be in, every single interaction they could have, also their age, also their comorbidities, also whatever could affect various parameters that are involved in this progression of the disease. And you also put in as many compartments as you feel there are details you want to keep track of. You want to keep track of asymptomatic versus symptomatic, serious disease versus non-serious disease. So, I mean, there are a lot of choices to be made here, and this entire range from agent-based models to just the very basic SIR type model. Where do you want to be in that range, and where is it sensible to be? And all of the answer to that, I'll just come to you in a second, depends on what question you're asking, what data is available, and whether you can sensibly do models with the data you have at that level and answer those questions. Sorry, yeah. They are kind of similar, except that, so usually when you use the stochastic, term stochastic, you're sort of talking about intrinsic stochasticity in all of these different events that you're putting in. Whether it be movement from in one compartment to another, that is one infectious state to another, that's stochastic, or movement from location to location, or things like that. Sometimes people talk about events when they also want to model sort of external imposed things like lockdowns and stuff like that. So if there are external events that are going to come in at a certain interval or even once, but are going to be imposed from outside onto the system, then sometimes people call that event. But essentially, you can use them interchangeably, because even the internal noise, a lot of it is because of events like A moved from this location to that location. Now the whole spread is going to be different. Yes?
There's just one more doubt. You're saying that in the stochastic or agent-based models, people tend to add this noise. But how do they quantify? Like, do they have any sort of set parameters?
Again, there are some ways, there are some standard ways in which you put certain kinds of noise in. So for instance, the noise in moving from one state to another, like from S to I, if you have sort of an infection process which is given by an average rate, then there are certain standard ideas about how much stochasticity will be around this. Okay, a rate is sort of already defining the fact that you can define a rate means in a small time interval there's a certain probability for it to happen. So if once you know the probability for an event to happen like this, you can ask over a longer period of time how much variability will there be. So that kind of thing you can put in fairly standard ways.
Okay.
But in other things, other kinds of stochasticity you actually have to measure. Like how much is the stochasticity in sort of a person going from home to workplace? Now that very much probably depends on the person, it depends on the population, it probably depends on which town you're in, what workplace you're talking about, who. There are some people who have a lot of variability in their going from home to work, they don't have fixed times. There are others who have very fixed times. So some of the stochasticity is really something you do have to go out and measure. Some of it, because it's mechanisms that you sort of understand, you can sort of guess the stochasticity, even if it's not been measured, like this kind of movement from susceptible to infected. But in some cases, you just don't know. You have to measure. And in some cases, that data is there, but in some cases, it's not there. So when it's not there, people make sort of assumptions and put something in, right? So I mean, it's very important in all these kind of models, when you read about them. I mean, I imagine many of you, even if you don't make the models, will be dealing with models that are talking about systems you're working on, or will be reading papers where modelers have tried to make predictions about some system you're working on. It's very, very important to really look very carefully at what assumptions they're making, what data they've actually have, how they've chosen parameters, how they know whether something is stochastic or not, and how much, and so on, okay? So, I mean, my point here is you can, I mean, the overall range of the types of models is really extreme. You can go all the way from agent-based, really detailed, lots and lots and lots of parameters, to something very simple. Each has their own pluses and minuses, okay? And you have to be well aware of that. So, what I wanted to do, I mean, we've not even gone into various things like, multiple variants that people have done, vaccinations, all sorts of stuff. You can put in so many things in these models. And people have. But this is just to give you a sense of just the whole range. How much you can go from very simple to very complicated. And what I want to do in the rest of this is to sort of again go back to this question that in the case of COVID as an example, people were very, very interested about predicting, right? Detailed predictions of where is this peak going to come, when is it going to come, and so on. So I want to tell you a little bit about the pitfalls of using models to make these kind of predictions. And COVID was a very, very good example because people were really involved. They were tweeting, they were making models left, right, and center, and everyone was tweeting their predictions. So I'm going to pick out a couple of tweets, but I mean, I also don't want to, so there was this Indian supermodel, which came out at some point. I don't want to really single out any one. There were many people doing lots of modeling, which had a lot of pitfalls. But this one was so obvious, I kind of feel like I have to show it to you as an example. So this was a tweet from, so this is sort of, huh? I kind of didn't want to. No, it's fine. No, it's not a secret who made this model, but so this is the first wave, right? This was the beginning of the time where the first wave was sort of down, and you were starting to see hints. So data here is up to about here somewhere, I think. And you were starting to see a bit of the second wave coming. So this was, I think, a tweet from, so this is March, right? Beginning of March in 2021. And the prediction was for a nice a little bit of an increase, and then it'll go down again. And this model, as you can see, this model gave a pretty good prediction. I mean, a pretty good retrofit to the data up to that point. great, and that's what it predicts. Huh? So that's, remember, this is beginning of March. About 20 days later, the data has already started showing a bit of an uptick, and now the model starts to show a bigger thing. Of course, you can't suddenly, this is clearly not the same model as this one, so something has changed. So something changed, but now the model now fits this little extra increase, and there's a bigger peak. And now very confidently, people are predicting, it'll start peaking around early to mid-April, and you'll get about, so, the prediction here was a total increase, no, somewhere here, yeah. So about 70, 80,000 new infections, and the peak was, supposed to hit well below the first wave peak and go down by quickly. Then the data starts coming in further, and that the model starts being modified to peak. But look, in all these cases, the model is fitting beautifully up to that point, and then giving some peak, and then new data comes in, and they tweak the model, and then a new peak comes, and the peak is slowly going up, and it's going up. At this point, they're saying the peak value will be sort of a little bit beyond the first wave peak, and now the model is now showing that peak. In all these cases, it's nicely fitting, okay? Beautiful fits. This is better fits than you'll find in, I've worked on other biological models, and I never see fits like this, okay? Excellent fits, but the prediction is basically running with the data, and you're seeing new fits. And you know what happened, right, finally? Here at this point, you're still predicting say maybe 1.5 times. This is the real trajectory. The real trajectory was about 4 times that peak, right? So what is happening here? At any given point, you have a model, it nicely fits the data up to there, and you make a prediction, and then a week later, little more data comes in, not even a few days later, sometimes 1 day later. There's new data, and now the model is predicting a different peak, and then a different peak, and then, so clearly this is all completely useless, right? No one should believe a model like this, no one should use a model like this to make a prediction, because in hindsight you can see it was completely pointless, right? Nobody got anything right about this. And the reason why the model is fitting the data so well is when you look more carefully at the paper, you find that basically they're using different parameters at different times, all right? So of course, if you use different parameters at different times, you can pretty much get what you want. And this is the final thing, and this was the final actual peak in around June, right? Where after the peak, there with the new data, it's again, the model is fitting very well, okay? So, it's again this question about parameters, right? Uma raised this question about parameters. How well do you know your parameters? And how well can you get your parameters from here, just the early part? So clearly, whatever they could do, the best fit with the parameters there was not doing very well. Then more data came in, and the parameters changed, and so on. And so, you have to understand when a model is actually going to be predictive and when it's not. And that is very different from whether it's fitting well or not. And that's the basic point I wanted to make. A well-fitting model doesn't necessarily mean anything. Okay? You have to understand why the fit is there, why is it fitting, and if it's fitting because you're tweaking your parameters to keep going with the fit, then clearly it means nothing, right? By the way, I didn't mean to single out just this one model. Many, many models were made, and most of the models were unable to predict anything significant about this fact, right? There are, as we discussed with the Ross model and so on, there are many qualitative features and many interesting things and many things about conceptualizing the problem and understanding that there could be a threshold that one does get from these models. But predicting a specific curve and where it peaks and when it will peak and when it will come down is very, very hard with these models. And these models typically will get it wrong. Why is that? So it comes back down to this exponential business that we talked about, right? So to repeat again, we can understand this even from the SIR model. And I want you to try and play with the SIR model later and try and understand this yourself. we had this very simple model, and let's assume there is a disease that is following the SIR model. Exactly. Forget about all the complications. Let's say there is a disease that follows this. As we've discussed, it is going to be exponential in the beginning, right? The fact, and I'll reiterate this, the fact is, let's go to these models. At the very beginning of a disease, the number of susceptible people is pretty much the whole population. So this is close to 1. So you have a case in which the rate of change of your infectious numbers is proportional to how many infections there are at that moment. Anytime you have some situation like that, rate of change of a quantity is proportional to how many there are at that moment, you have an exponential process. When you have an exponential process, it is very, very sensitive. There's a particular rate that depends on the parameters and so on, but suppose the rate changes a little bit, an exponential process is a process that really takes off. And small changes and small errors at the beginning of an exponential process can get amplified. So here's an example. This is just a little test case. I took an exponential with a certain rate, okay? And that exponential is this black curve, and I just picked out 4 points. So, let's assume this is supposed to represent how an infection spreads over, say, about 20 weeks. But I have data for the first 4 weeks, which comes directly from this exponential. So I take this exponential, I calculate it, and I add 10% error, just randomly. Okay, it so happened that these 4 points that I computed from this exponential with 10% error happened to be, a couple of points happened to be a little above. If I did this again, a couple of points might have been a little below, or 1 point might have been above, it's totally random. It just so happened that a couple of points were above. If I fit this, the best fit that I get, I know it's exponential, I have this data, I know there's 10% error, but I do the best I can. I make the best fit. And it's a pretty decent fit up to this point. But if I continue for 20 weeks, I go way off. So this is the real exponential, and these were the points. And it just so happened that the first couple of points early on both had errors in the same direction. And that was enough to throw my prediction off a lot. And as we've been discussing, there is stochasticity in infections, right? And not only in infections, in measurements. We are now talking about taking data from a real disease that's spreading and trying to infer back parameters of a model. And in this case, it's like the simplest possible model. It's an exponential. I even know how much error there is, but I can go very wrong if just by chance a couple of data points have errors in the same direction. Because exponentials are such amplifying behavior, small changes can get amplified, and that's what makes parameter estimation difficult. So if it's difficult in this case, you can imagine how difficult it is in a complicated model like the previous models we were talking about here, and why they had to actually use so many different parameters at so many different stages of the model, because they just couldn't fit it. So it's this exponential thing that really causes problems with infectious disease and estimation of parameter values. It's part of this is what was happening here. Over here, there's a little bit of data over here from which this has been extrapolated. Here, you get a little more data, so you have a little better idea of how far up it's going. But errors here, small errors, can totally change whether this peak goes up to that much or whether it only stops over here. And this is the problem that was happening with this model, that exponential processes are just really, really hard to estimate. And it's part of a more general thing. So in general, complicated nonlinear systems, so exponential is a very simple case of a situation where small changes are amplified. But there's a very, very general theory, which we now understand. There are a large set of systems which are just complicated and nonlinear enough where small differences are amplified. So this model is a very, very simple model, which was made by a meteorologist. So he was thinking about the convection of air in the atmosphere of the Earth, okay? And of course, that's a complicated system, right? How does air in the atmosphere circulate over scales as large as the Earth is a very, very complicated problem. There's lots of processes. Yes?
that's largely driven by the people tested, right?
Yes, yes, absolutely.
So how's that controlled? I mean, like right now there is no testing, so you can't really.
No. So exactly. I mean, the point is the stochasticity is there even intrinsically in the spread. But on top of that, when you're actually trying to estimate parameters, you're estimating from sampled data, and there is noise that comes in from the sampling. So there are so many sources of noise. And this is why basically, because there are so many sources of noise, and very early on in an exponential, if there is a slight deviation in one direction or another, you will just totally misestimate, where this exponential is growing. This is why it's very hard. And so, I mean, it's a genuinely tough problem to actually estimate parameters for an exponential process like that.
The question I would rephrase in a way that, say, if the government is doing the testing,
yeah,
based on these models, can we say that there must be these many numbers of tests must be done, say in the city or ward or whatever?
Yes.
That in order for us to say how things
Yeah.
are changing.
Yeah. No, so absolutely. I think, again, you can. So in the context of a given model, if you believe that that model is a reasonable description, you can certainly say what kind of data and what, how much error I can tolerate in the data and still get a decent estimate. But as it so happens with exponential processes, I think it's fair to say that this kind of level of precision, the kind of level of precision that practically you would get, even with any government really taking this seriously and providing data and keeping track, there would still be enough error that you probably would not be able to predict more than a few weeks in advance. Like, you could probably predict a week in advance or 2 weeks in advance. Anything beyond that starts to get very, very difficult, even with the best of intentions. So forget about if you don't even have that structure. So my point was, this is actually known as a feature of certain kinds of complex dynamical systems. And it's just, you should know that it's exponential is one type of system which has this prediction problem. But there is a large class of systems which are nonlinear in a certain way. And it was first discovered by this guy, Edward Lorenz, who realized that, if you have a simple kind of nonlinear system, so this is supposed to describe, a very simplified version of the convection of air in the atmosphere. And this X is some kind of measure of the convection flow, and these are measures of, the temperature difference at different places in the atmosphere. And you see this complicated behavior. But the key point is that if you start two trajectories off with these equations, and now we're not even talking about the atmosphere, we're talking about really a model with 3 parameters, completely deterministic model. You start them off with very, very, very close to each other. So you choose X, Y, and Z values very close. And for a long time, the trajectory, it's complicated, but it follows. But eventually, it separates. And you can see this sort of, you start 2 trajectories very close to each other. Eventually, they follow each other for a while, but eventually, they just separate. And the point of this is that if your precision in measuring your initial state is, some amount, is larger than this, you will never be able to predict properly the long-term behavior of these kind of systems. You just can't. Simply because these systems, like the exponential, essentially take small differences and expand them. And this is the problem with infectious diseases and many other systems like weather, that small differences, which are going to be very hard in practice to actually get data that is with that precision or less than that precision, they sort of limit how long you can actually predict a system for. So since we're talking about weather, and as an analogy to infectious disease, how do people deal with this in weather? We know people make weather predictions, right? And you know how weather predictions are. Weather predictions are a complicated, I just wanted to say, if somebody wants to read more about this, this is a book which is a nice, more popular introduction to this idea of chaotic dynamical systems. And this is a more mathematical introduction. So if you want to read more about these chaotic systems, do look at these books. But how does weather prediction work? And the one key thing, and which is a lesson I think one can take into infectious diseases, is almost no one in weather prediction works with a single model and tries to make a prediction. It's always an ensemble of models. Many things vary between. So, wherever you really see proper serious types of weather prediction, you will always see predictions with error bars. You will always see predictions from a large number of models. So for instance, this is like, hurricane, tracking hurricanes, for instance, and predicting where a hurricane will go. Again, a complicated nonlinear phenomenon, very, very hard to predict. But the way people try to do it as best as they can is to take many models, and in these models, vary initial conditions, vary parameter values, vary the kinds of processes that are included or not included. What would be the equivalent in infectious disease? Let's say you were looking at compartmental models. You would actually ideally like to have people working on all sorts of different models. Very simple compartmental models, very complicated models, doing the best they can to put in the data as much as they can. Where they don't know the parameter values, exploring a range of parameter values, and getting a sense of the range of dynamical behavior you can get. And what you would predict is not what a single model does or says, but you would predict a range across a whole range of models. And very likely, some aspects of that would not be useful. There would be such a large range that beyond, as I was saying, a week or two, and this is true in case of weather also, sometimes beyond a week, people really can't make weather predictions very well. In certain parts of the world, that may be a little longer and weather is more stable and you can make predictions for longer. In some cases, you can't. And this is the same for infectious diseases. Even with an ensemble of models, you may get some average idea, but if the spread is too large, it won't be a sensible prediction, but at least you'll know it's not a sensible prediction. So the advantage of looking at ensembles of models is that you get a sense of the range and the error in your predictions. And at least that tells you whether to take a prediction seriously or not. Okay? So that's a much more sensible, I think, approach towards actual predictions of very, very fine-grained data about how cases are going up and down, would be to take some lessons from weather prediction. And I haven't even talked about, both in the case of weather and in the case of infectious diseases, we've been talking about dynamical models, models where we are effectively, by having these compartments and these infection states and these rules about how does a susceptible get infected, we are actually trying to model the mechanism. There are a whole different class of models, which I'm not going to get into, where you're not bothered about the mechanism, you're just trying to extract correlations. You want to make predictions about how cases go up and down, but based on purely on correlative data. So essentially statistical analysis of lots of trajectories or lots of data from different locations that you have before, okay? So that's a completely different approach, and it's related to machine learning approaches. I mean, machine learning, any of you might have been hearing about, right? And it's getting used in a lot of different cases. It's also being used in these kind of situations, where essentially you're taking lots of trajectories of a disease and trying to learn from that using this kind of black box that then can spit out some prediction, okay? It's very different from what we've been talking about, which is, we've been talking about dynamical models that are actually trying to model the mechanism underlying. So just keep in mind that there are also that kind of model, and that kind of model is also used in weather and so on. And people, again, as I said, when they try to make predictions, they make a prediction across all these different kinds of models. So when using an ensemble of models, they use both these kind of causal models, as we've been sort of talking about, as well as these correlative models, which are just pulling out purely statistical behavior. Okay, but let me just mention, it's very important for you to keep in mind that all of these models, however complicated they may be, are nevertheless making various kinds of approximations and assumptions. So always keep in mind and try to ask these kinds of questions. What kinds of predictions, or what kinds of questions is this model trying to answer? What questions is it appropriate to answer? What questions is it not appropriate to answer? A very simple model certainly cannot answer questions about a very complicated or detailed bit of behavior. On the contrary, a very complicated model might be able to answer that question on the face of it, But you have to ask what kinds of parameters are they using? Where are they getting those parameters? Do they have enough knowledge about those parameters to make that prediction accurately? So what data is available to reduce the uncertainties? And very importantly, what time and length scales are these models sensible for? So in the case of weather or in the case of infectious disease, does it even make sense to use these models to make predictions 1 year later? Probably, I mean, almost certainly not. Does it make sense to make it a month later? Maybe, maybe not. Depends on the disease, depends on what's happening. A week later, now you're starting to talk. Maybe a week later, yes. Maybe very often you can. So this is important. And it's very important to keep into account what processes are included or not included. In all these models, we can keep adding layers. There was so much happening in something like COVID. There was movement of people. There was also change of behavior of people as cases went up and down. There was, of course, imposition of things like masks and so on. But whether people took an imposition seriously or not seriously also changed with time. Now, how are those processes to be put in? Do they matter? So again, it's important to keep all these in mind. On the face of it, it looks like, there's just too much going on and models are never going to help. But they do in some cases. And so let me sort of come back to this after having spent all this time saying, all the problems with making predictions. Let's come back to some of the ways in which models are actually useful. So I talked about, very simple models, even in a situation where there's not much data, have this great use that they conceptualize the problem. They tell you about key combinations of parameters, and I hope the SIR model sort of gave you some sense of that. But one other thing that models do very well is to tell you what does not work. And I think people underestimate this a lot. There is a lot of information. People spend a lot of time talking about fitting data, fitting models to data, and talking about, oh, this is a great fit. But when something does not fit, when a sensible model does not fit, that's actually really, really useful. So I spent a lot of time telling you how this was a very bad way of predicting what's happening. But the most interesting part of this model, I thought, which was actually really useful information, was the fact that they could not fit this. Even the first wave, or forget about the 2 waves and the 2 variants, but even the first wave could not be fit by this model with a single set of transmission parameters. That means, why is this useful information? The fact that it could not be fit is actually a very strong statement, much more interesting than the fact that with all these parameters you could fit it. That's not interesting. Why is it interesting? Because now it raises a lot of interesting questions. Now you can ask, what are the processes that then make transmission probabilities change with time, right? You can ask, can you model them? Can you collect data about this? Can you actually track the change of this parameter over time? Is it because of change of the way the virus is behaving? Is it the change in the way the people are behaving? What kind of processes are behind this? On what timescales and length scales do these processes act? Suddenly there's a whole new set of questions you ask. So sometimes the point of a model is not to necessarily predict something, but to raise the sensible questions to ask after this. And that's something I like. The other thing that models at whatever level of this whole range we've talked about, with even simple ones, with their lesser parameters, but many simplifications, or very complicated ones with all the realism, but some trouble with parameters. All of them actually can sometimes be very useful for comparison of scenarios. Okay, so I'll give you a couple of examples of that, because that's a way in which I often work with models. Even if you're getting something about the base process not quite correct, or let's say, to put it in a more positive sense, if models are just an approximation of the base process of how this disease is progressing, and maybe they're not the most appropriate for predicting exactly how it's progressing, they may still, despite the approximation, be a very good tool for comparing different scenarios. So in the context of COVID, for instance, many people were interested in what interventions one should do to try and help, right? When you're comparing different kinds of interventions, it is useful to use models to compare. So let me give you an example. So here is one case in which we took this pretty complicated model, okay, of COVID with all these compartments, asymptomatic, pre-symptomatic, all sorts of stuff, because we were interested in some of this. We also had some data on the age stratification and so on. So we took a model with all of this stuff. And what we wanted to do, so this was on the scale of these different models I've been talking about. It's more towards the fairly complicated side, less towards the more simple SIR models. So it was actually more like a network or agent-based model, where we actually had locations, we had workplaces, we had homes, we had people moving between them, and this kind of a model just purely computationally can handle sort of about a population of about 1 million. So what you're trying to do is maybe a small town, or something on the scale of a small town. So one can start looking for data, and there is in fact data about workplace distributions and so on, independent of COVID, for certain kinds of small towns in India. And across various towns, there are certain qualitative features that are reasonable. So one can take some of this data and make a kind of a network picture of how many people there are in this small town, how many different kinds of work locations there are, and so on, and have people moving around with some simple rules of how they move around, how often they move around. Let's say people go to work and back once a day, roughly speaking, things like that. So one has some idea of the ranges of many of these parameters. There are many parameters one still doesn't know, but one can make some educated guesses. So we have a system of like about 1 million people, okay? Each of these people are in different locations. Within each location, you sort of have this kind of a compartmental model going on, where people get infected, they take a little bit of time to get infectious, they might be asymptomatic or pre-symptomatic, they might get seriously hospitalized and die, or they might recover, and so on, okay? And if you take this kind of a system, and now you want to test out different kinds of strategies, right? You want to say, what will happen if you're testing people at some rate, and you're asking, based on these tests, if they get tested positive, they should stay at home, or their entire home should get quarantined. You can test out various different scenarios. So the point is, do you see a difference in these scenarios on this basal level model that may or may not be a very accurate simulation of COVID, but has some features of it and has some features that probably don't match. So again, in this kind of comparison, so here's one of the things we find. So one of the interesting questions was, you remember at the time of COVID, there were these PCR tests and these RAT tests, right? So essentially, there was a test that was kind of the gold standard, that was supposed to be very accurate, but it was a pretty complicated test to do. You needed someone reasonably professional to do it. You needed the sample to go to a lab. It usually took some time. You'd probably take a few days for the result to come, right? But if you got tested by that was considered the gold standard. It was a very accurate test. On the other hand, there were these home tests you could do, which were considerably less accurate, okay? Sometimes remarkably low accuracy compared to like even random, okay? Little bit more accurate than random. But on the other hand, they were fast, they were quick, you got the result immediately, and you could act on it immediately, right? So the question here was, in a scenario of a spreading infection that is as close to COVID as we could make it, what would be the impact of these two? Which would be better? Would it be better to use tests that were harder to do and would take some time to give results and have some quarantining or isolating strategy based on that? Or would it be better to use these quick and dirty tests? And if so, how dirty could they be? How low resolution, how inaccurate could they be and still be useful? So essentially, we tested this out on this sort of spreading infectious disease and tried out different kinds of testing and quarantining scenarios, right? And in all this, because the underlying system is still an approximation of COVID, one should be careful and give more weight to predictions that are qualitatively very strong. Predictions that are small, quantitative little differences, maybe that, all the approximations that go in don't really. But if you see a strong effect somewhere, that's actually very important. And the strongest effect we saw was actually, so what's shown here is each one of these are, for every value on this x and the y axis is a different simulation. And what we plot in each of these simulations is a certain test sensitivity, and how many of the tests were these quick and dirty ones, how many were the very accurate ones. And based on the testing strategy, different strategies for how you isolate and so on. And essentially how many were infected. So in all this, the lower you are, the better, right? So total fraction infected, you want to keep that as low as possible, right? You want less people infected. So just the way to read these graphs is, where on this graph are you as low as possible? And it turns out that, what was most important was not whether you're doing RAT tests or PCR tests or whatever. The most important thing was actually how many tests you're doing, right? The total number of tests was by far more important than anything else. So irrespective of all the approximations and everything, you could change parameters, you could tweak everything. The one qualitatively very strong statement you can make is, forget everything else, just test as much as you can. But having said that, now then you can ask a more graded question. Now you can ask, okay, so if you are testing reasonably often, would you rather use lots of RAT tests, which are quick but relatively ineffective? Or would you use lots of PCR tests, which is over here? And of course, using PCR tests is better, but as soon as you get a little delay in the results, it turns out that is overturned. So the takeaway from this was, yes, we might be using an approximate model of the infectious disease spreading, but a couple of things that don't depend on so much on the approximation, because you can change the parameters and you still get the same qualitative result, is one, just test as much as you can. Whatever strategy you have for isolation, the details doesn't matter. Do some isolation based on testing, but test as much as you can, and try and get tests that give you results quickly, even if they're less accurate. So this is what I mean by sort of using a model as a comparison. Okay, I'll give you one more quick example, which is again when vaccines started coming in, right? When vaccines started coming in, there was this complicated protocol of how vaccines will be given, who will be given to, then will be given, and when you do one dose, when you do the second dose, and stuff like that. There was all sorts of procedural issues that had to be sort of sorted out. Yes.
Could you please go back to the previous slide? All this assumption would only hold true if the number of false positive would be more rather than false negative. Yeah. Did you account for that? Because logically,
so this totally, the sensitivity sort of takes care of one of the things, and then there's the other aspect. Right?
I mean, sensitivity.
Yes.
I mean, quantitatively looking at it, it only says how the prediction is, how wrong but it doesn't qualitatively say which is a false positive, which is false negative.
So you can also take that into account. Okay. So in this case, actually with the RATs and the PCRs, we had reasonable data of both of that, right? We had data on all of them, right? The false positives, the false negatives, we had all of that. So you take that into account. And there were different RAT tests available. And the idea was to sort of compare those. That's basically what, so along this axis, essentially the difference between the different RAT tests was mainly in their sensitivity. So you can totally take all that into account. I mean, you can make a more complicated figure from the same model, which would be harder to show on the plot. But essentially, you could test all this based on the false positives, false negative rate, the false positive rate, and all of them separately. So yeah, you can totally take all that into account. So I'm just summarizing some of the things that came out which actually had a qualitative result. Okay, yeah. So the other thing was another very situation where comparison was something we were interested in, was what kind of vaccine strategy should you do and so on. And there were so many things about it, right? Should you give it first to people with comorbidities? Should you first give it to people with that? You have a limited number of vaccines doses available, how should you distribute it. So again, one can imagine various scenarios that one can compare. And again, on the same model, so we compared different kinds of things. And again, I'm summarizing all of that with essentially a couple of the more stronger statements that came out. So this is the point. In these models, given that they're always approximate, you have to also see which of the results are the stronger, more robust results, and which are the more fine, but therefore less robust results. So you should spend time sort of thinking about the more robust results. So the robust result here is, again, when you think about the various aspects of vaccination strategy, there is the vaccination efficacy, there is first dose efficacy, second dose efficacy, there is also the rate at which you can vaccinate, there are a limited number. So which of these parameters are most important? It turned out, of course, in some ways this is not surprising, but the rate at which you vaccinate had by far the most effect. It turned out that the first dose efficacy had by far more effect than the second dose. So it really, the biggest effect happened if you got a lot of people vaccinated with even one dose. The second dose was not as big a deal. Whether that happened or a little bit later, a little earlier, or it had little more efficacy or less efficacy, were all little details, relatively smaller details. The big effects were the rate of vaccination and the rate at which, and the first dose efficacy. And it in fact did not even matter very much how you distributed it amongst the population. So, it tells you a little bit about sort of, the point here was to sort of tell you that comparison of scenarios can still be a very effective way of using these kind of models, whether more on the more complicated end or on the more simplified end. So it turns out, I told you all of these plots were from a fairly complicated model, but then we went back to even simple models and actually tested the same sorts of questions in simpler models to try and understand, whether the simpler models show the same results, and they do. So that's what I mean by a strong, robust result. So when you're comparing different scenarios, again, it's important, just as I said with predictions, to compare across an ensemble of models. There's almost literally no point taking a single model in these kind of complex scenarios where data is not always there and parameters are hard to fix. There's no point taking a single model and trying to do either very complicated predictions or very complicated comparisons of scenarios. Comparison of scenarios is a very useful thing you can do with models, but again, it's useful to do it over an ensemble of models and see which result is most robust. Which result sort of seems to be true across a range of models with more or less whatever parameters, at least the best you can do. With simple models and with more complex models, if you're getting the same result, then that's a stronger statement that you can make. So the use of models in all these things is actually very useful, but needs to be taken with a pinch of salt and needs to be done in a way where ideally you use a range of models to try and make your predictions, whether they're predictions about comparisons or predictions about specific behavior. Okay, so let me kind of end with that. And I think we have about an hour. And I thought what would be nice, now we've discussed so many things, what would be nice is to go now to the applet and imagine that is a real disease that is spreading. And somehow that's data you have access to. And there are many things you can play around and try to understand about that. You can look at the applet as a simulation of a model. And just, so those of you who are interested in models and just want to understand how a model works, the applet tells you something about that. But I think it will also be kind of instructive if you think of it as a real disease and some porthole to real data, and think about how, if this was the disease that was going, how you would extract something. So for instance, if you open the applet, let me open the applet. Sorry, maybe before I do this, is there any questions about all this? Any more questions that anybody has? You can come back and ask questions in between also. Yes.
Like, how did they take this values of drift, beta? Did they?
Yeah, I actually didn't read the paper in enough detail to tell you that, but oops, as far as I know the beta they estimate by sort of fitting, like essentially fitting small ranges and thinking of them as exponential and getting some sense of, what kind of exponential you get and back calculating beta. So that's one question. That's actually something you can do with the applet also. I would, in fact, one thing you can do. So I'm going to list a couple of things you can try and do with the applet. Sorry, did that answer your question? Yeah, the drift, I actually don't know how they got it. So, but we can look at the paper. But this gives me a good idea. Yes, go ahead. Pass this.
Yeah, so you mentioned stochastic events throwing off the model predictions. So how often has that happened in disease dynamics? Because I would assume that if we can't pinpoint the process, it would hardly really throw you off. Yeah. Because even in that model, there was some variant and that can just tell you that, yeah, this model is not working, or maybe this model will work till some variant comes into picture.
Sure.
So in disease dynamics, how often does that happen that you can't pinpoint the process that is causing?
Yeah, I mean, in some sense, you're always making an approximation to the process. That was one of the points I wanted to make. The model is always an approximation. Maybe a way of thinking about it is, so how good is that approximation? I think that's what you can try and pin down. It turns out that I think it seems that many of these models, and with parameters that people manage to find or fit, you can actually get decent fits to past data. That seems pretty clear. You can get a reasonable sense of what processes are happening and have happened in the past. But to extrapolate from that into the future is where it's very hard. So in some sense, you do know, I think we have a fairly good idea, like in COVID. See, it's also never only about the model. One should not use the model as the only way of trying to understand what process. It's always a combination of that with medical knowledge, with other kinds of work, with other kinds of experimental epidemiological work, where you get a sense of the processes. So, I know with COVID, we know this, right? People were working a lot there was a lot of controversy about whether it's because of, what size droplets, and is it aerosol, and so on. And that, of course, is not, there's different kinds of models were involved there, but it's not compartmental models that then uncovered whether you were having aerosol transmission or not. So you do need to combine a lot of information from a lot of different sources to get to the processes. In some sense, the models are not the best way of ruling in processes. They're good ways of sometimes ruling out processes or ruling out simple combinations. If you put together a simple combination process and it just does not fit, then you know that's not it. There's got to be something more going on. So that's why models are useful. They're useful for saying it's not just this when it doesn't fit. When it fits, you can say, yes, it could be this combination. This is one way of looking at it, but there could be more things going on also. Did that sort of answer your question? Yeah. Okay. So, so in fact, from both the questions, there are a couple of possibilities about what you can do with this applet. Let me put the applet up, and then we can. Has everybody got some access to that applet? Here's what happens. So let me tell you a little bit more about it, just so you know. This is basically an SIR model, except that I've added some stochasticity to it. So instead of modeling these three equations, we are actually modeling 10,000 people. And these 10,000 people are essentially doing these chemical reactions. It's essentially like modeling a little chemical system. So there are S-type molecules and I-type molecules and R-type molecules. And when an S and an I molecule collide with each other, there's a certain probability that the S will become an I. Okay? So susceptible and infectious people meet each other at a certain rate, and that rate multiplied by the probability gives you the transmission rate, which is equivalent to this beta over here. and the recovery time is 1 over gamma, okay? So it's really essentially this, and with 10,000 people, it's very close to the deterministic equations. The trajectories you get are very close, but I'll just show you. If you run the applet again, it shows you a trace of the previous trajectory. So you can see in light color the previous one, and you can see some amount of stochasticity, right? So this variation comes because each run is stochastic. Each run, some events sometimes happen a little more quickly, some a little more later. And so sometimes the peak is here, sometimes the peak is a little further along, and sometimes the susceptibles fall a little quicker, sometimes a little later. So there are some variations, but overall it doesn't look very noisy either because there are 10,000 people. So there's this, I chose this because it's essentially pretty close to this, okay? But it has a little bit of stochasticity, you can see. And so one can try to explore now a couple of different things, okay? So you can change these. Just remember, more practically, if you actually change something on, like if you make the 14 into 7, you have to press enter. If you move the slider, it changes it, but otherwise you have to press enter. And then you can run this again, and now you see a big difference. So now this is not a stochastic difference. This is a difference because I changed the recovery time, right? So this is a big differences like this from the previous run are because you changed a parameter. But if I run this again now, then you'll see something very similar. So now, you don't even see very much stochasticity, it's very little. These numbers will change a little bit, but you'll see, okay? So depending on the parameters also, you might get more or less stochasticity. If you make this much smaller, let's see what happens. Now it takes a longer time, and you might not even see an infection spread. So here might be a case where you've actually gone to an R0 that is less than 1, okay? So in earlier cases, we were seeing R0 larger than 1. That's why an infection was really spreading, and you would see a peak. Here, you really did not see the infection spread at all. So by changing parameters, not surprising, we saw that R0 depends on beta and gamma. So of course, by changing beta and or gamma, you should be able to get to R0 less than 1. So here are a few things you can try and play with, okay? One kind of thing, for those who are just interested in the model, you can try and understand some of this behavior. You can try and see, so what are the things we discovered about the model? We discovered that only this combination should matter, right? It's only the ratio of beta and gamma. So if you change these numbers around and keep the ratio the same, you should really see very similar behavior. What should be different? You might see a difference in the time scale, because in making these equations, we had tau equals beta t. So beta does come in. So if you change beta, but keep the ratio of beta and gamma the same, you should see very similar behavior, but it might happen a little slower or a little later. So that's, some things like that you can test out. You can test if R0 is larger than 1 and the infection spread, if R0 is less than 1, does it die out? But these are all modeling things. One other completely interesting thing, which might be interesting for many of you, is imagine, as I was saying, this is a real disease, and this is sort of just your portal on some information you can get. So imagine that I was someone who was following this infection, and I wanted to make some predictions. I pick some numbers for the transmission rate and the recovery time, but suppose I didn't know what the transmission time was. Suppose I started this, and I had only run it up to here. Or let's say, let me do it a little more fast. Sorry. Okay, let's say I'd only run this infection up to here, right? At this point, I know how many recovered. Let's say I had tests, and by sampling, let's say, here you have all the information. You have exactly how many recovered exactly. But in a realistic scenario, what would you do? You'd have maybe 100 tests. You throw out 100 tests, and you'd get some samples. And from those samples, you'd sort of recalculate. You'd get some idea of how many are infected there. So let's say you had 100 tests here. It seems like 1,000 out of 10,000 are infected. So, if you had 100 tests, maybe you got like 10 people infected. Then you'd estimate, okay, so about 1,000 are infected. And similarly, you can find out, from the seropositivity, you can find out how many have recovered. Suppose you had these numbers at this stage. And suppose very quickly after that, if you say restart and then pause again very quickly, now you have numbers at another time. Can you go back and from these numbers estimate beta? And will you get a good estimate of what is here, 0.3? So I think that would be a nice exercise for some of you to try. Try and get 2 data points. And now, given what you know about what we've discussed about exponentials and so on, can you try and back calculate beta and see how close you get to 0.3? So how easy is it to calculate? In this case, you know the underlying process. I've told you what it is. I've even told you the parameters. But suppose you didn't know, and all you had was the trajectory, and maybe even just 2 data points. Could you estimate it? Could you estimate it with 3 data points better? Just how much wiggle room is there? And I think what you'll get a sense of is what I was talking about these exponential processes and how hard it is to estimate their parameters. That was a very simple case of an exponential, and I was just adding some error. Here's a real case of an SIR infection spreading with some error, and you can get some sense of how hard or easy it is to back calculate the actual parameters. Okay? So remember, as we said, the initial increase should be exponential. We kind of calculated the exponential a little more carefully with beta and gamma. So if you can calculate that exponential rate of increase and you know gamma, then you should be able to calculate beta, right? So is the problem clear? I'll just repeat it once again. Take the applet, run it for a really short time, right? And pull down the numbers and the time. Then let it run for a very short time again and pull down the new time and the new numbers. From those 2 data sets, can you calculate the exponential increase, assuming it's exponential? Can you calculate beta? Okay, so that's the first exercise I would like you to do. Yeah, go ahead.
No, our points are in which phase, like it's in log phase or not?
Yeah,
is it
so you don't know exactly. Again, see, imagine this is a real disease playing out in front of your eyes. Okay, so you don't know exactly what's going on. You have to try and infer that. So how would you infer that? So the question is, it's a great question. How do you know it is an exponential? So one question is, given the data points, assuming it's an exponential, can you back calculate beta? The second question is, how sure are you that it is an exponential? How well can you figure that out from 2 points? Can you figure it out from 2 points? Or do you need 3 points? If you need 3 points, try do 3 points. And then do it with 3 points. Can you get a better estimate and a better sense of whether you are in that exponential phase or not? So play with it. If it's running a little too fast for you to actually stop in time, as it was happening with me, you can make it considerably slower. So if I do this, it really goes slowly, and you have lots of time to pause and take down data points, and then pause again, and so on. So I would like you now to start playing with this. Yes? Sorry, maybe so that others can hear. Somebody has the...
Hi, so are you using Euler's scheme for solving this or something else?
No, so actually, for those of you who know, I'm doing a sort of a Gillespie version of this.
Okay.
A Gillespie version of the...
So slower and... so this is...
Slower and faster is
because the time step difference?
No, it's not that. It's just slower and faster is just to allow you to go slower. There is a time step difference that comes in, which is why I've written that the slower is a little more accurate and the thing is faster. There's a sort of a version of a way of sort of speeding up Gillespie, So essentially, the slowest version is just really Gillespie.
Okay.
Okay, and then in order to make it a little faster, we do a little approximation, which allows bigger time steps, which then makes it less accurate. So it's technically then not Gillespie, but it's an approximation. So what I would like is all of you to try this exercise. In case it's unclear, let me write it down. Let me write down what I want you to do. And what I would like is different people or different groups, you can work in groups also if you like, to start telling me estimates of what beta they got and what beta they actually used. So it'll be nice to get a sense of how much error you're seeing. So run the applet for different times, for say 2 different times. So you'll have sort of T1, T2, S1, S2, I1, I2, R1, R2. From this, estimate beta given, let's assume you're given gamma. Let's say you keep gamma fixed to whatever you like. You know what gamma is. You get these times and these numbers and estimate beta. And compare it to the beta that you actually used. Is that clear? And then the third thing is you can add another set of times. S3, I3, R3, and from all of these, estimate how close to exponential is I of t. Feel free to discuss with each other also. Huh? There's no, it's not like a test. Yes. Use the value in the applet. Like you pick some values for gamma and beta, and let's assume that is something you know, because that is, let's say somebody has done an estimate, gone to many places and seen the recovery time. So let's say recovery time is often easily estimated, right? Over a large population in hospitals, people will know how long it takes to recover. So let's say you know gamma. So use that gamma value itself. Use the gamma, but assume you don't know beta. You've used beta to get this data, but you don't know beta, and you're trying to figure out what beta is. Yes? Yeah, I mean, if that's what you've used, feel free to change it. Nobody needs to stick with the default numbers here. If you want to try with 1 over 10 or 1 over 14 or 1 over 5, do whatever you like. In fact, that would be nice. Yes? Sorry, say again. How much are you getting? So you're getting 0.26. Let me just write down some of the things that people get. So what it should be, beta used and estimated. So one person has got, so I guess you used 0.3 and you got 0.26. Not bad. Let's see as others see how much variation it happens, and we can try and understand. 0.18 and you use 0.3, right? Okay, so good, we're getting some sense of what you get. That one's almost half. Yeah. If you use, I mean, if you use the, Well, let's just hold on to these numbers for a bit. Then we'll try and figure out why some have got more accurate than others. We can try and figure out what happened. So just let's get a few more numbers in.
I just substituted
Yes?
to this formula. This is what I'm doing is right.
Yeah. Nothing wrong with that.
For a total number of infected was 25 at time period 8.
Good.
So I0 was 10 because at the initial number.
Yes, you put 10. That's good.
Exponential beta I kept unknown.
Gamma is 1/7. Yeah, 1/7. Yeah, keep track of the units. So are others also getting close to it? Yes? 0.31. Nice. So these are all 0.3 and somebody got 0.31.
Go further in time.
Yes.
After this crossing point.
Yes.
We'll getting lower and lower.
Absolutely. So that's one of the things, yes. No, indeed. It only works if you get it early on. So let's see. Is anybody having trouble getting a number? Like anybody confused about how to even proceed? You're confused about how to proceed? You're confused? Okay, there are a few. Can one of you who did it, can I call on you to show what you did? Will you come down? So 0.26. I think you can rub out most things. Well, you can at least rub out on the left, if that's enough. Yeah. Maybe you should take the mic.
Right. So we have an infection. Let's say at I0 it's 1, and I'm just setting this up. So at I10.
Anybody?
Okay, I don't have the values.
You can stop him at any point.
Hello. Oh, okay.
Just hold it closer.
Can someone give me a value of I10? Or?
No, why don't you, do you have the values you yourself picked up?
Yeah,
go get
Can you give me
Use
the values
you got?
So I'm recording my infection, number of infections at time unit 10, 37. And I20 is 128. So at time 10, I have 37 infected individuals. And at 20 time unit, I have 128 infected individuals, right? So now, we have this IT is I0 gamma minus beta, right? No, beta minus gamma, I'm sorry. In transmission, right? So it increases exponentially at the start of the infection. So we want to, cut it out before it reaches the saturation. But anyway, so now...
No, these are all important points because somebody may not have. So 20 was early enough, 20 was somewhere here, right?
Yeah.
So he didn't go too far in the infection, okay? And some of you may have gone further. So we'll see. That'll be interesting to compare. If some of you have gone further, what they got. Go ahead.
Right. So now I'll just, so I want to use 20 and 10, right? These are the time units that I have. So since it's an exponential distribution, it only depends on this t, and there's a constant, right? And then you have the starting point. So let me just say that my starting point is time equal to 10. And I want to evaluate it at time equal to 20, right? So which is essentially, so I'm calculating it for a difference of delta t, like, the time unit is 10 units, right? So my starting point is 10, and I want to find what its value is at 20. Like I know it, so I want to evaluate the beta, right? So beta minus gamma, this will be 20 minus 10, right? Because I'm calculating it for like after 10 days. So beta minus gamma into 10. So I have I20, I have I10, I have gamma, I can find out beta, right? which is...
Does everybody understand that this 10 is not the same as this 10? This 10 is a difference between the two.
Yeah.
It's because if he had 25 here, it would have been 15.
Right.
But this would have been 25 and 10, right? Everybody understood? This 10 comes from the difference in times.
Maybe I should write delta t over here. Oh no.
Yeah, that's fine. No, it's okay.
Okay, so now let's just rearranging it. So if I put this at the bottom, so I20 by I10.
And what did you use for gamma?
7 days, so 1 by 7.
1 by 7.
So gamma is
remember to use 1 by 7, okay?
That's the rate, right? This is the rate.
Okay. The rest is rearrangement. The rest is just calculation, right? Everybody got this? Is this what everybody done? Not everybody has done this. I know at least one person has done something slightly different. Okay? But it's fine. Is this what everybody did? Just use, okay. But does this make sense? Right? So this is certainly one way. Another person, I think, didn't even necessarily need I20 because they had I10 or whatever time they had, and they used the fact that the initial numbers was 10, which is something in the applet. But the reason I was actually asking you to use 2 data points is because suppose it had been a real disease, you may not know what I0 was, right? So this technique, this at least allows you to get rid of I0. You don't have to worry about I0. We don't know, right? COVID in some little district, you know some of the numbers along the way, but you don't know if it was 0 or I0 was 1 or 2 or what. Maybe very often it is 1, but it doesn't have to be, right? So this one doesn't use that. So okay, great. So you got this. So you got 0.26. In your case, you got 0.18. What was different? Was anything different? What do you think was different? What were the times? No, he didn't in the end. He didn't in the end take 1 because, I mean, he started off saying 1, but he actually didn't use it because he used this formula. He didn't use this formula really. So what was your times? He used 10 and 20. Yeah? Yeah? Time was 49. So you used 2 times or just 1 time? Oh, you use 1 time. You use 1 time and you use the initial. So let me put it this way. He used 2 time points, 10 and 20, and he used this formula, which was for the difference of times. You used 1 time point and the fact that the initial was 1. Is that correct? Right? And your time was 49. So you used I0 equals 1 and I49 equals something, right? Oh, sorry, 10, yeah. You used I0 10, which was kind of given in the applet, but in any realistic scenario that would be, you would actually not have access to that. But let's say you measured it and you got I10 and this you used 49. So one difference here is that he went up to time 20 and she went up to time 49. Let's look at the applet and see where is 49 and where along the curve are you. So where's 49? Let it come. 49 is kind of, 49 is, that's 100, so that's 40, so it's somewhere around here, I guess, right? Right? So it's further along. So he used 20, and that's 40, and 49 is somewhere here. So that tells you something. It's something another person raised. One, you got a more accurate reading in the initial part if the time was less, and you got a less accurate reading if you used a later time and assumed the exponential. Why is that? Because the exponential assumption gets less and less true. And as you reach the peak over here, of course it's not. So, it's exponential up to a certain point and then it starts bending over. So of course, if it bends over and you assume that it was exponential up to there, you would have, so let me try and draw this. So if this is the exponential part and then later it bends over, but you have a time point here, and you think this was the exponential, you would assume the exponential was something like that. So you would get an exponential that's growing slower. It would have to. Because if you use the real growing exponential, that would shoot off too high, right? So as a result, that's why you got a much lower value. If you pull your time back down, you'd get a more reasonable value. Yep. Yeah, because if you take 104, you're well past the exponential, right? And then you're really much lower. So then if you go beyond the peak, of course, and you think this is then exponential, the exponential that would hit that would be something like that, right? So clearly, you have to try and stay within the exponential part. So the next question, which would be the second part, would be how well how do you know if you're in the exponential part or not? Okay. So for that, I mean, 1 point is actually not enough, right? If you didn't know this curve, all of you know this curve, that's why you can kind of see it. But suppose you didn't know it, you have to imagine this is all happening in the background somewhere and you're just getting those data points. If you didn't know the curve, you wouldn't know if this is an exponential. How many points do you need to know if it's an exponential? If you had, say, so let me get rid of this point. If you had this point and this point, would you know if you've gone past? Maybe. If you can't fit the same exponential to here and here, right? But if you had 2 points, just these 2 points and not the initial starting point, then you would be lost because you could find an exponential that goes through here, right? So you need at least 3 points. Either you know the initial one and 2 more points, or you need 3 points to know. So one thing you could try and do is try and get 3 sets of numbers and then try and plot it and see how would you plot it to see if it's exponential. There's one very simple way is to try and plot log of I of t versus t. If it's exponential, this will be a straight line, right? And how do you know? If it's a straight line, if there are 2 points, then you can always put a straight line through it. But if there's 3 points, you'll know if one of the points is off, right? You'll know if it's close to a straight line or not. So that's one way of telling if you're in the exponential regime. So if you take 3, so one good thing to do, one exercise you can try and do in the next 10, 15 minutes is try and see up to what point the exponential remains. So take samples. So you're taking samples, and you're keeping on plotting this. And as you take samples initially, for small times, we know up to about time 20, this was not a bad estimate. So probably up to time 20, it's not too far from exponential. But at some point, it'll stop being exponential. And then what will happen? So maybe the first few, so you take it 5, you take it 10, you take it 20, you should see a straight line here. So time versus log of I, you should see a straight line. But at some point, something should start happening. What will happen to this curve? It'll start bending over, right? It'll deviate from a straight line. So that's the point at which you know that you're no longer in the regime where you can use this simple way of calculating. Then you need a more complicated way of calculating beta. But try that. So what I would like you to do, those of you who've done the first part, try and figure out at what point do you start deviating from this. No, you can't. So you'll have to do that yourself. Yeah, that would be easy. Yeah. Yes. That's already, yes, you're right. By then, it's definitely not exponential. So by the time you've reached the peak, you're definitely not exponential. But actually, you will find that the exponential deviation, the deviation from exponential happens well before that. The peak is already quite far. It's where you've bent over and already almost 0. But actually, so how far back? So the point is, I want you to see whether the deviation happens. Where did I leave the pointer? Yeah, so the peak here is around, so the peak is around here, right? The peak is around 40 maybe in this simulation. But does it already happen at 20? Does it happen at 30? Where is it happening? Anybody else got any numbers for estimates for beta?
0.194.
Okay.
T is equal to 13, I got 0.204. And for T is equal to 18, I've been getting 0.18.
Okay.
I don't know.
Yeah, no.
My vague estimate.
Okay, not bad. So you have to think. Yes.
Take the 2 points and we shifted the time frame and get the slope of the.
Yes, what do you want to do with it? Oh, when it becomes, yes, so
When it becomes.
so when the slope changes. Yeah, absolutely. That would be fine. So if you keep taking 2 points, and the slope is the same as what you calculated, then it's when you're in the exponential. If it changes, but it's easier, so that's kind of what you're seeing here, right? In this plot, this is the slope. Here it's the same slope. Here it's the same slope, but then it deviates. So it matches what you're seeing. For those of you who want to try something a little more advanced, one thing you could try and see, as I told you, this is a stochastic simulation, right? But stochastic doesn't mean that there aren't any patterns. So one interesting thing you could try and see is where the stochasticity comes in and what effect it has. So one thing stochasticity does is it makes the peak come earlier or later. What correlation does that have to the final infected? Does the peak coming earlier mean that you get more infections or less infections, finally? Is there a correlation or not? These are kinds of questions you can ask. Yeah, what do you think that will tell you? Do you think the peak is always there? That's an interesting question. So this is something an interesting question has been raised. Is the peak always where these two intersect? That's something you need to play with. In this simulation, it looks close, but it looks a little bit beyond to me. But you should run it a few times and try it with different parameters and see. Yeah, so one thing you can do is try and figure out where does the exponential part stop being exponential. I mean, where does it deviate from exponential? If some of you have done that part also, one thing you could try is everyone has seemingly stuck with the same default parameter values, which give you an R0 of 0.3 into 7, which is about 2.1. So it's larger than 1, but how sensitive is this estimation, even if you do it in the exponential regime, to R0? So try different parameter values and see what if R0 is very close to 1, let's say it's 1.1, or what if R0 is much larger? Does it get easier to estimate or harder to estimate? Is it easier to get, even if you stuck with the same times, was it easier? Would you get a better estimate of beta if your R0 was large or if R0 was small? So is a very rapidly spreading disease easier to estimate parameters for? Is a very slowly spreading disease easier to estimate parameters for? Sorry, when you're increasing what?
Then we're getting easier.
Then it's yeah. So there are two things, I mean, that you have to think about. One is that with R0 larger, the exponential will be steeper. So in some ways, you have more range to get good numbers. But the other problem is it's also quicker to reach the peak. So your time is shorter. So these are trade-offs. In some case, it may be easier, but in some cases, maybe a very high R0 makes the time in which you have this exponential so short that you don't have time to estimate it properly. So it's not an obvious answer, actually. So that's why I want you to experiment and find out actually what happens. So I guess it's almost lunchtime. So you guys can keep playing with this. Are there any questions, any final thoughts anybody wants to? Yes. Yeah.
Where you asked us this question that how
R naught.
Yeah, so that we did.
Yes.
So if R naught is 1.1, it is basically those two curves, they just run flat.
They run flat. It's too low. So you have to try something harder. Fine. Yeah.
If the transmission rate is very high, where then the curve suddenly dip and it is
Yeah.
easier to kind of have where exactly the distance will peak and
Yeah.
where exactly the infection.
You're getting a better estimate. Good, good. Okay, great. Great. Yeah, yeah. So these are not obvious answers actually, even with the SIR model. So some amount you have to play. So maybe just final thoughts. I hope you got some sense of what these models are about. And please keep playing with the applet as you like. I think it'll stay up on that server for some time. But more than that, I think what I want you to take away from this is sort of the huge range of sort of types of models that exist, even with compartmental models, the ways in which people can complicate them. And exactly as Uma had pointed out, every complication comes with extra parameters, and there's always this trade-off. If simple models have very few parameters, you could actually probably get decent estimates of those parameters, but they miss out on many processes. More complicated models have all the processes, but have so many parameters that you probably miss out on. So how does one, deal with these trade-offs? And I hope you got a sense from playing around here of how you might start to begin to estimate sometimes parameters from data. Okay, it's just the very beginning, but you can already see that it's not so easy. That there's many features, in some sense, assumptions you have to make about the model, underlying model. If you have assumptions about it, then you can make some estimates. But if you change those assumptions, the estimates would change. So, keep this in mind all the time whenever you're working with, even if you're not doing models yourself, you'll often be working with predictions from models, or people think, say, based on models, or parameter estimates that come from certain underlying model that may or may not be actually verbalized properly, maybe there somewhere underlying. So it's always important to keep asking, what are the assumptions that have gone into anything that comes out, whether it's a prediction of a model or a parameter estimate that comes from something like that. So if there's one thing I want you to take away, it's that models should not be treated as some kind of oracle which just tells you the answer. They all are approximations. It's just what kind of approximations, how good of an approximation, are they sensible or not sensible? These are questions you have to ask for any kind of model you ever come across with, even if you're just reading about it. Okay? Any final questions? Otherwise, I guess we can just stop and go for lunch. At earlier, yeah. So great, exactly. So one of the things you can get some sense from SIR models is, qualitatively speaking, how does the initial numbers affect, when does the peak arise? How does the different parameters affect how high the peak goes? And these are, as qualitative statements, they are still very useful, because it gives you some sense of some basic progression. Whether this actually is a good prediction in any specific disease or not may or may not be true, but it does, even the qualitative idea of the overall progression of a disease is very important. And it's important to know which stage you're in. Are you in the initial stage where it's still rising exponentially? Are you in the stage where it's slowing down? Are you past the peak? And the question of what kinds of interventions you might do and might be relevant in these different stages are true, even if your model predicts the specific thing or not. The stages are something that is true for all kinds of diseases. And it's important to think about, what are the relative differences between these different stages, and what kinds of things you need to do to manage an epidemic depending on which stage you're in. Okay, great. Okay, thanks very much. Thank you.